Now we will look at soft actor critic. So this is where we start with soft actor critic, or SAC for short. The idea behind this algorithm is pretty straightforward. It's a reinforced learning method that works off policy, and at the same time it tries to keep the agent exploring by encouraging high entropy in the policy. That just means it doesn't want the agent to be too confident or deterministic too early. And now let's look at the architecture. Here we can see. Okay, so up at the top here we have got the stochastic policy network. This part is where actions are sampled from. You will see it's labeled as Gaussian policy. That means instead of giving you one fixed action, the network gives you a distribution and actions are sampled from that. So when you see this, I'm pi as, that's just notation for the probability of taking action a given state as prime. And underneath that we have got this entropy value showing. You can see right now it is saying around 2 and now 1.80. Anyway, this gives us a sense of how random or exploratory the current policy is, and it is marked as updating, which tells us the policy is being trained as we go. Okay, and below the policy network we have two Q functions, also known as the Turing critics. These are estimating the expected return, in other words, how good an action is, and having two of them helps reduce bias during training. They are both updating, which means they are being trained with fresh experience coming in. And here at the bottom, there's this temperature coefficient labeled as alpha. You can think of this as a knob that adjusts how much randomness we want in the policy. If alpha is high, we favor more exploration. If it is low, the policy becomes more deterministic. And right now it is around 0.26. We can say here. And we can see that's the auto tuned, right? That means the algorithm itself is adjusting it based on how much entropy it wants to maintain. And on the bar, you can see it visually sitting closer to the middle, leaning slightly toward exploration. And it is changing. Okay, let's move on and let's talk about algorithm flow. And here's our flows or steps. This sequence here shows us what steps the SAC algorithm is cycling through during training. And each color represents one step in the loop. We start with sampling an action, then collect experience, store it in a buffer, sample batches for training, and then go on to update the critics, the actor, and the entropy coefficient. And uh, sample action, what's going on here is that the agent is using the current policy, the one we just looked at, to generate an action. And because it's a stochastic policy, it samples this action from a Gaussian distribution. And so even if you are in the same state more than once, the action can vary a bit, which keeps things exploratory. And in the last step here, we can see the algorithm was on tuning entropy. That's when it updates alpha, at the temperature we talked about, to try and keep the policy at the right level of randomness. If entropy drops too low, not entropy, the temperature might go up. And if entropy is too high, the temperature gets reduced. So it is always balancing that. And that's the general structure. And that's okay. And maximization is here. All right, now we will talk about uh, the core objective behind SAC. What you see here is the main formula that the algorithm is trying to optimize. And it is written as J of pi equals the expected sum of rewards plus alpha times entropy of the policy. And let's break that down. The first part, the expected sum of rewards, is standard. That's what most reinforced learning methods go after. But SAC adds something extra here, and that's the second part, the entropy term. What it does is encourage the policy to stay uncertain or spread out for as long as possible instead of locking into one behavior too early. And that's controlled by this parameter alpha. If alpha is large, if alpha is large, it puts more emphasis on entropy, meaning the agent explores more. Okay, if it is smaller, the focus shifts more toward maximizing reward directly. And what's nice is that SAC doesn't keep this fixed. It tunes alpha automatically to try and hit a certain entropy level. That's okay, I hope. And here we have got a slider that adjusts the temperature manually for illustration. And you can see our values like that. And let's make it 0.23. And based on that value, the policy distribution you see underneath shows how the actions are spread out. With lower temperatures, the distribution tightens, the policy is more confident. And with higher values, it spreads out more, meaning the agent is more exploratory. And let's go over to the advantages of using SAC. First thing is sample efficiency. Since SAC works off policy, it can reuse past experience. It stores data in a reply buffer and samples from that, so it doesn't have to interact with the environment constantly to learn. And the second thing is exploration. Because it explicitly includes entropy in the objective, the agent is encouraged to explore in a structured way. And it is not just random noise, it is guided randomness if you want to think of it that way. And another point here is robustness. One thing that's useful when you are training these models is not having to tweak every single parameter endlessly. SAC tends to be less sensitive to hyperparameters compared to some other algorithms like DDPG or PPO. So that's helpful if you are not doing a massive tuning process. And finally, it supports multimodal policies. That just means the agent can learn more than one way to handle a situation. So if there are multiple good strategies to complete a task, SAC can learn several of them, not just one fixed behavior like you will get from a deterministic policy. So that's what makes SAC flexible and pretty reliable, especially in continuous control problems. And that's all for this lesson, and thank you for listening.